Good morning, learners and viewers. Welcome to the session for Quantitative Analysis for Managerial Application MMPC 005. We are in Block 2, and today we will be talking about Unit 5, that is basic concept of probability. We are continuing for last time. We were talking about this numerical, how to calculate probabilities in complex situations. The problem given to us is in a survey, it was found that 21 people liked product A, 26 liked product B, and 29 liked product C. If 14 people like product A and B, 12 people like product C and A, and 14 people like product B and C, and 8 liked all the three, then how many liked product C only? We will assume that there are three sets of people, A, B, and C, and they like product A, product B, product C, respectively. Going back to the problem, we see that A liked 21. For B product, there are 26. For C, it is 29. A intersection B, because A and B both are included, there are 14 people. For C and A, there are 12 people. And for B and C, there are 8 people. There are 14 people. But there are 8 people who like A, B, C, all. That means in that case, we will be writing A intersection, B intersection, C. For this particular problem, we will be drawing basically a Venn diagram. Here, there are three products, A, B, C, so we will be drawing three circles, A, B, C, and they are overlapping each other. So in that case, we will be finding out how many numbers are there with intersection. We will start with A intersection B. There are 14, but there is a third condition, that is A intersection B intersection C. In that case, we will be subtracting 14 minus 8. In that region at the top, we will be writing 6. And similarly, we will be performing for all the remaining two parts. In that case, we will be getting this, what we can see in the Venn diagram, that 6, 4, 6, and 8 is common to all. Now we have to find how many people like product C only. So in all, we have 29. We will be subtracting the summation of 4, 8, and 6. So we get 11. That means there are 11 people who like product C only. Now we consider another problem, which is conditional based. Consider your locality where out of 5,000 people residing, 1,200 are above the age of 30 years and 3,000 are female. Out of the 1,200 who are above 30, 200 are females. Now, suppose that a person is chosen and you are told that the person is a female. Then what is the probability that she is above 30? Now we can see that there are two conditions simultaneously given in the problem. And first of all, we have to convert this condition into a mathematical notation. So we will say that A be a person who is chosen above 30 years of age. B is a person who is a female. Problem is focused on the event A. Given that B has occurred. In the last line of the problem, it is that we have to find the probability that that means a female above 30. If we denote the event by A by B, we want to find probability of A by B. Out of 1200 people who are above 30, 200 are females. This is given to us in the problem. Now here out of 5,000 people in the locality, 200 possesses the characteristics of being female as above 30 years. Now, event AB can be defined as AB event that a person is both female and above 30 years of age. So, here what is going to change? A will be a person chosen above 30 years, and B is a person chosen as a female. That means PA will be 1200 by 5000, PB will be 3000 by 5000, and PAB will be 200 by 5000. Now, we have to find that it is given that it is a female which is chosen and she is above 30 years. So we see that there are 3000 females in the total population. Only 200 are females and above 30. That means the required probability is 200 by 3000. And your answer will be written by probability A by B equal to 200 by 3000. There is another method of writing this. It can be written in this way also. A by B is equal to 200 by 3000. That is the answer. But how it came? It is basically PAB by PB. That is 2000, 200 by 5000 into 5000 by 300. That is PAB is 200 by 5000 and PB is 3000 by 5000. Exactly the answer is 200 by 3000. Now we move to axioms of probability. In axiomatic approach, probability is introduced as a function of outcomes of an experiment under certain restrictions. These restrictions are known as axioms of probability. Axiom 1 is the probability of an event is a non-negative real number. That means it will be between 0 and 1 for any subset of A of S. Mathematically, it can be written as 0 is less than PA less than equal to 1. The first axiom implies that the probability of an event is a non-negative number less than or equal to unity. Axiom 2 is PS equal to 1. The second axiom implies that the probability of an event that is certain to occur must be equal to unity. How do we assign probabilities to events? There are a few theorems on probability which will help us in mathematical treatment of the subject of probability. Now we will see what they are. Theorem 1. Probability of phi is 0. That means phi is a null event. The event is not going to happen. Its probability is 0. P A bar. That means negation of A. It is equal to 1 minus PA. Or we can say that A bar is the complement of A. Theorem 3. For any two events A and B in a sample space S, probability of A negative intersection B will be equal to probability of B minus probability of A intersection B. A intersection B means the common. Theorem 4. Addition of probabilities. Probability of A union B is equal to PA plus PB minus P int A intersection B. Then comes your conditional probability theorem. For any two events in a sample space S, the probability of their simultaneous occurrence is given by PA intersection B is equal to PA into PB by A or PB into PA by B. PB by A is a conditional probability of B given that A has already occurred. Then comes your multiplicative theorem. It's applicable for independent events. If A and B are independent, then the probability of their occurrence simultaneously is given by P A intersection B is equal to PA into PB. The next theorem is Bayes' theorem. This is one of the most important theorem as well as mostly applied theorem in the practical area. Before starting the theorem, it is imperative to know about prior and posterior probabilities. Prior probabilities, these are the probabilities which are assigned to events on the basis of conditions or the past experience or the judgment. And posterior probabilities are the revised probabilities in the light of some additional information. Now we will see how these are applied in Bayes. Bayes' theorem states that if A and B are two mutually exclusive and collectively exhaustive events, and C is another event defined in the context of the same experiment, then given the values of PA, PB, PC by A, and PC by B, the conditional probability of PA by C will be PCA C by A into PA upon summation of PCA into PA and PCB into PA. Similarly, if we have to find PB by C, so in the numerator, it will be PCB C by B into PB upon summation of PC by B into PA plus PB plus PCB C by B into PA. Now we will see how this is applied. Suppose a car manufacturing factory has two plants, A and X and Y. Plant X manufactures 70% of the cars, and plant Y manufactures 30% of the cars. 80% of the cars of plant X and 90% of the cars of plant Y are rated of standard quality. A car is chosen at random. It is found to be of standard quality. Then what is the probability that it has come from plant X? We start the solution that we assume that E be the event that the car is of standard quality. Let B1 and B2 be the events that the car is manufactured by plant X and plant Y. If we have to calculate PB1, it is 70% of the quality cars. That means 70 by 100, which is equal to 7 by 10. Second plant is plant Y. We have assumed that it's PB2. Its probability will be 30 by 100, which is equal to 3 by 10. Now, a car has been selected and it is of quality, standard quality. That means if it came from plant X, it will be written as PE by B1, which is equal to 80 by 100, which is equal to 8 by 10. And similarly for plant B, it is PE by B2, which is 90 by 100. On simplification, we are going to get 9 by 10 while solving the problem of Bayes theorems. Always try to keep your denominator a same number throughout the problem. That will be easier for you to simplify the problem. Now see, I have taken 10 everywhere. We have to find the probability that a standard car was chosen and the condition is that it came from plant X. So your answer will be PB1 by E equal to PB into PE by B1 upon summation of PB1 into PE by B1 plus PB2 into PE by B2. We will write out the numbers. You can see that in numerator as well as in denominator, the LCM is same, that is 80. So we can leave it in the numerator. In numerator we are getting 56, and in denominator's numerator will be summation of these two numbers, that is 7 into 8, 56 plus 27, which comes out to be 83. That means without solving, much solving, you got the answer as 56 by 83. Similarly, if the problem was that the probability that the standard quality came from plant Y, so we will just be replacing the numerator by the probability of plant Y. Now we move to unit 6, that is discrete probability distribution. If all the possible outcomes of an experiment together with their chances of occurrence are made available, so we can use this distribution. If batting on head, you find that a toss of three coins may result in 0, 1, 2, or 3, with the respective probabilities of 1 by 8, 3 by 8, 3 by 8, and 1 by 8. We'll see it how we got these numbers. This representation of all possible outcomes and their probability is known as probability distribution. Suppose you are interested in number of heads in tossing of 12 coins. You need to apply a discrete probability distribution. Discrete probability distribution can be used in decision making. Outcomes of toss of three coins are expressed in terms of number of heads, that is denoted by H. An H can assume the value of 0, no head, 1 head, 2 head, 3 head, corresponding to each of the values, which is the probability associated with the outcome. This uncertain real variable H, which assumes different values depending on the outcome of an experiment, and to each of whose values a probability assignment can be made, is known as random variable. A discrete probability distribution counts occurrences that have countable or finite outcomes. This is in contrast to a continuous distribution where outcomes can fall anywhere in a quantum. Common example of discrete distribution includes binomial, Poisson, and Bernoulli's distribution. A discrete probability distribution function has two characteristics: that each probability is between 0 and 1, both inclusive, and the sum of the probabilities is 1. We are talking about discrete events, and these are those with a finite number of outcomes. That means tossing dice or coins. For example, if we flip a coin, there are only two possible outcomes, head or tail. When we roll a six-sided die, we can only obtain one of the six possible outcomes. That is one, a number of 1, 2, 3, 4, 5, or 6. Basically, it is computed as mu is equal to summation of product of x into probability, that is px. The variance sigma square and standard deviation sigma of a discrete random variable x are numbers that indicate the variability of x over numerous trials of experiment. Now, we write normally in this way. So we have probability and distribution of number of heads. If we talk about heads, so as I said, no head, 0, 1 head, 1, 2 head, 2, 3 heads, 3. These 0, 1, 2, 3 are discrete values. And the probability, one no head means 1 by 8. That is 0.125. One head is 0.375. Third one, two head is 0.375. And three heads is 0.125. This what the numbers are probability distribution. And when we sum them all, we get 1. Now how it is written, the exact way of writing it. We are in to probability distribution of a random variable. A description giving the values of a random variable along with the corresponding probability is called probability distribution of random variable. If a random variable x takes the values of x1, x2, x3 till xn, and their respective probability is p1, p2, p3 till pn, then mathematically in a table order form it can be written as x in front of, we can write x1, x2, x3 till xn, and px, that means the probability of the event, that is p1, p2, p3 till pn. Now, the above probability distribution of x can defined only be when each p1 is greater than or equal to 0. That means the probability exists. And the summation of all the probabilities, that is from 1 to n, is equal to 1. That is the confirmation. And that confirmation is used when we are solving of the problem that we have calculated the respective probabilities correctly. Now, the second step is to calculate mean and variance of random variable. The mean is denoted by mu. It is equal to Ex, which is equal to summation of the event and the respective probability. Then comes your variance. Variance is denoted by sigma square, which is equal to summation of x square pi minus mu square. Mu square means mean. The standard deviation is the under root of the variance. Variance is defined as the expected value of the square of the difference between the random variable and its expected value. Now, we will see how mathematically it is used. We have to find the mean, variance, and standard deviation of number of heads when three coins are tossed. First of all, we will write sample space. All the three tails, two tail, one head, tail, head, tail, 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 head, tail, head, tail, and head, head. These are 8 in number. We will write ns equal to 8. Now we have to assume that the problem wants mean, variance, and standard deviation of number of heads. That means x will be the number of heads in tossing 3 coins. The number of heads may take the numbers as 0, 1, 2, or 3. Now, we have to find the respective probability. If there is no head, that means we will be having all the 3 tails. It is seen that in one case only it is there, that is PTTT. Total number of favorable cases 1 and total number of cases are 8. That means the respective probability will be 1 by 8. When x is equal to 1, that means you are getting 1 head when 3 coins are tossed. So from the sample space, we will find it out how many conditions are there where a single head has appeared. That means a single head with 2 tails. There are 3 conditions, so that will be the probability of getting 1 head will be 3 by 8. Third one is x is equal to 2. That means you are getting 2 heads. Again, going to the sample space, we will see that there are 3 conditions where we are getting 2 heads. And in the third case, we will write the 3 heads. There is only a one case where we have 3 heads, that is 1 by 8. Now we will be writing them in the tabular form. X is 0, 1, 2, 3. P1 is equal to 1 by 8, 3 by 8, 3 by 8, and 1 by 8. First of all, we have to check that summation of P1 is 1 or not. In this case, it is 8 by 8, which is 1. That means we have evaluated the probabilities of the event correctly. Second step is to find the mean. That is mu equal to summation xi pi. That means you will be multiplying 0 by 1 by 8 plus 1 into 3 by 8 plus 2 into 3 by 8 plus 3 into 1 by 8, which comes out to be 3 by 2. Second step is variance. Variance is summation. Sigma square is equal to summation of x square pi minus mu square. Now, x square means you have to square 0. 0 into 0, any number will be 0, leave it. Second one, 1 square is 1. 1 into 3 by 8 is 3 by 8. 2 square is 4. 4 into 3 by 8 is 12 by 8. Plus 3 square is 9. 9 into 1 by 8 is 9 by 8. Minus mu square. Your mu is 3 by 2. 3 by 2 square is 9 by 4. After evaluating, you will get 3 by 4. Now we have to find standard deviation. Standard deviation is under root of variance. That is under root of 3 by 4, which comes out to be root 3 by 2. Now we move to second part, that is Bernoulli's theorem. Let there be n independent trials in an experiment, and let the random variable x denotes the number of successes in these trials. The probability of getting a success in the single trial will P, and probability of getting a failure with Q. We know that P plus Q is equal to 1. That means summation of success plus summation of failure is 1. Now, we will be using a relation FR is equal to NCR, P raised to the power R, Q raised to the power N minus R. Now the question arises how to evaluate NCR. NCR is basically opened by factorial. NCR is equal to n factorial upon r factorial into n minus r factorial. We have to write the observations in tabular form. We have values of x as 0, 1, 2 till r, and we have to then find the respective probabilities. So we will be using the relation NCR PR raised to the power PR into Q raised to the power n minus r. In this case, when r is equal to 0, it will be Q raised to the power n. When r is 1, it will be npq raised to the power n minus 1. When r is 2, it is nc2 p square q raised to the power n minus 2. And in the last, you will get ncr pr q raised to the power n minus r. This is the mathematical relation for binomial distribution. Now the question arises, where do we use them? We use Bernoulli's theorem, Bernoulli's process in coin tossing and success and failure situations. Condition for application of binomial distribution. The experiment is performed with fixed number of trials and performed for finite trials. Second one, each trial must give either a success or of a failure. The probability of success in each trial is same. Here also we have three things. That is mu is equal to np. Variance is sigma square is equal to npq, and your standard deviation is under root of variance, that is under root of npq. Poisson process and distribution. Third one. Poisson distribution is applicable to events occurring randomly over a time and space. Represents distribution of several relative variables like to count the number of defectives of a finished product, to count the number of deaths in a country by any disease or natural calamity, to count the number of infected plants in the field, the number of bacteria in the organism, or the radioactive decay of an atom, or to calculate the waiting time between the events. These are the conditions where Poisson distribution or a Poisson process is applied. Now, what is the relation mathematical formula for that? Poisson process corresponds to Bernoulli's process with a very large number of trials and with a very low probability of success, that is m by n. M by n is equal to p, or we can say that m is equal to n into p, and r is the number of successes. So for relation for finding out the probability is PR is equal to e raised to the power minus m into m raised to the power r upon r factorial. Now what are the properties of Poisson distribution? Here, the events are independent. The average number of successes in the given period of time alone can occur, and no two events can occur at the same time. The Poisson distribution is limited when the number of trials n is indefinitely large. In that case, mean is equal to variance and it is equal to lambda, where lambda is the product of n and p, which is a finite number and it is a constant. The standard deviation is always equal to the square root of the mean. Now we will see how practically it is applied. If 3% of electronics units manufactured by a company are defective, 3%, find the probability that a sample of 200 units, less than 2 bulbs, are defective. So here we can see that the probability of defective bulb is 3 by 100. That is 3%, which comes out to be 0.0003. And the sample size is 200. So here what we see, probability is very less and your n is too large. Straight away, this is a case of Poisson distribution. That means we have to find lambda. Lambda is n into p, which comes out to be 200 into 0.03, which is 6. Now, we have the relation for Poisson distribution as PR is equal to e raised to the power lambda minus lambda into lambda raised to the power r or x upon r or x factorial. So here we are taking x. So we have to find the probability of a sample of 200 units containing less than 2 bulbs as defective. That means it is denoted by px less than 2, which means either it can have 0 defective or it can have 1 defective. So we have to calculate px is equal to 0 and px is equal to 1, and we will be adding them. We will be applying the real formula e raised to the power minus 6 into 6 raised to the power 0 upon 0 factorial plus e raised to the power minus 6 into 6 raised to the power 1 upon 1 factorial. Do remember one thing, 0 factorial is not 0, 0 factorial is 1. The first one will be e raised to the power minus 6 and the second one will be 6 times of e raised to the power minus 6. To make it simple, we will be adding, so that means we can say that it will be 7 times e raised to the power minus 6. And the value of e raised to the power minus 6 will either be given in the problem or you can take it from the table, which comes out to be 0.00247. And now our answer will come, that is, we will be multiplying 0.00247 by 7. So we will be getting 0.01729. That is the answer. Now we move to unit 7. That is continuous probability distribution. As far as the introduction is concerned, this part has a variable region, or we can say that variable of interest may take any value within a finite number of values is called a continuous random variable. Probability distribution of such a variable is called continuous probability distribution. We will start with normal distribution. This normal distribution is the most versatile of all the continuous probability distribution. It is found to be useful in statistical inferences, characterizing uncertainties, many real problem processes, and approximating other probability distributions. What is normal distribution in statistics? A normal distribution is a continuous probability distribution that is symmetrical around its mean, and most of the observation clusters along the central peak, and the probabilities for values further away from the mean taper off equally in both directions. What are the properties of normal distribution? Probability distribution function of normal distribution is given by fx equal to 1 upon sigma times under root 2 pi into e raised to the power minus 1 by 2 into x minus mu upon sigma whole square. And its range from is from minus infinity to plus infinity. You have to remember a relation for normal distribution, that is x minus mu upon sigma. That's it. That is, we will be using as z score. Real world phenomena that actually follow the normal distribution. That is, birth weight of babies, height of males, blood pressure. What are its properties? Some of the important properties of normal distribution are: in normal distribution, mean, mode, median, all three are equal. The total area under the curve should be equal to 1. The normally distributed curve should be symmetric at the center. That means its peak value will be maximum at the center. There should be exactly half of the values on the right of the center and exactly half of the values on the left of the center. Or in probability terms, we will be adding them, we will be getting 1. Now we move to area under normal curve. The plot of fx versus x gives the normal curve, and the area under the curve gives its respective probability. The normal distribution is symmetric about the mean. Therefore, the area on each side of the mean will be 0.5. That means 50% on the left, 50% on the right. The empirical rule states that 99.7% of the data observed following a normal distribution lies within 3 standard deviation of mean. And the rule says that 68% of the data fall within 1 standard deviation, 95% falls within 2 standard deviation, and 99.7% within 3 standard deviation from the mean. The formula for calculating a z score is z is equal to x minus mu, where x is the raw score, mu is the population mean, and sigma is the population standard deviation. Mathematically, it is written as z is equal to x minus mu upon sigma. Here in the graph, you can see that at the center, it is at the maximum peak. And on the left side, it's coming down. The line is becoming parallel to x-axis. Keep one thing in mind, this line does not touch the x-axis. It's always above it. Normal distribution describes continuous data which have a symmetric distribution with a characteristics of bell-shaped. Binomial distribution describes the distribution of binary data from a finite sample. Now we will see how it works. A radar unit is used to measure speeds of car on a motorway. The speeds are normally distributed with a mean of 90 kilometers per hour and a standard deviation of 10 kilometers per hour. Now, what is the probability that a car picked at random is traveling at a speed of more than 100 kilometers per hour? Going back to the problem, you can see that it is written that the speed is normally distributed. That means this is a relation of a problem of normal distribution. And for normal distribution, you need mean and standard deviation. It is very well prescribed in the problem. Mathematically, we can write mu equal to 90, sigma is equal to 10, and your x is the random variable which represents the speed. Now, in the particular problem, you have to find out the probability that the car which is chosen is moving at a speed higher than 100 kilometers. That means you can write it as Px greater than 100. Your x is 100. So first of all, you have to determine z. Z is equal to x minus mu upon sigma, which is 100 minus 90 upon 10, which comes out to be 1. In terms of normal distribution solution, we have to write Px greater than 1, which means P is in terms of Z is greater than 1. We have to find the probability. So we can write P Z greater than equal to Z greater than 1 as the total area minus the area of the left of Z equal to 1. Z equal to 1 has value has to be taken from the table or it will be given in the problem. Writing the value of Z equal to 1 under normal distribution curve, it comes out to be 0.8413. From subtracting from 1, you are going to get 0.1587. That means probability of a car picked at random, which is traveling at a speed of 100 kilometers per hour, is 0.1587. What are the characteristics? Score of standard normal distribution is a standard score that indicates how many standard deviations are away from the mean on individual values x slice. When z is positive, the x value is greater than mean, z less than mean, and when z score is equal to 0, the value is equal to mean. Remember, z is equal to x minus mu upon sigma. The z score tells us how many standard deviations are away from the mean each value lies. This is a bell-shaped blue. I said it will be away above, somewhat above the baseline. It is not going to touch. As soon as it's moved away, the deviation comes into play. On the right hand side, we get the value of z as positive, and on the left side, we get the value as negative, and at the center line, z is equal to 0. Usually happening in the real world follows a normal distribution. This enables researchers to practice normal distribution as a model for evaluating probabilities linked with real world scenarios. Basically, the analysis includes two steps: converting the raw data from the scores of z score using the conversion equation given as z is equal to x minus mu upon sigma. Second one is finding the probability. After the raw data is transformed into z scores, then with the help of standard normal distribution table or normal distribution calculators available online to find probabilities linked with the z score. After the raw data is transformed, now we will see a problem. For some computers, the time period between charges of a battery is normally distributed with a mean of 50 hours and a standard deviation of 15 hours. Achal has one of these computers and needs to know the probability that the time period will be between 50 and 70 hours. Just have a look on the problem. We have used the word normally distributed. If it is a normal distribution problem, so it should have mean and standard deviation. Both things again are given to you. Now, you have to probably find the probability that the battery life is between 70 and 50. Now we will see. Let x be the random variable that represents the time period. The mean is given to you as 50 and standard deviation as 50. The sigma will be 50 and mu is 50. We have to find the probability that x lies between 50 and 70. That means probability 50 less than x less than 70. Now we will be transforming this data in z scores. So z for px is equal to 50. Z will be 50 minus 50 upon 15, which comes out to be 0. For z is equal to 70, It comes out to be 1.33. Transforming the basic equation from P50 less than Z less than P50 less than X less than 70 in terms of Z, we get P0 less than Z less than 1.33. As far as the area is to be calculated, it can be written as area to the left of Z is 1.33 and area to the left of Z is equal to 0. So we will find out the values of Z equal to 1.33 from the table and Z is equal to 0 from the table. As far as Z is equal to 0 is concerned, it will be zero point 0.5. And as the 0 point value of Z at 1.33 is concerned, it is 0.9082. So we will be subtracting it. We get 0.4082. That means the probability that Achel's computer has a time period between 50 and 70 hours is equal to 0.4082, or we can say 40%. We take up another problem to understand it, because here the condition is will be different. Most graduate schools of a business requires applicants for admission to take the Graduate Management Admission Council's GMAT examination. Scores on the GMAT are roughly normally distributed, with a mean of 527 and a standard deviation of 112. What is the probability of an individual scoring above 500 on the GMAT? So we can see that we have mu equal to 527 and standard deviation sigma is equal to 112. So first of all, we will find it out value of Z. And Z value, first of all, what is the value of X? X is 500. Your 500 Z will be 500 minus 527 upon 112, which comes out to be negative 0.24107. It is negative. That means it will be on the left side. So we have to write the solution now. Probability X greater than 500 will be equal to probability Z greater than negative 0.24. Negative 0.24 means this part. So we want the probability of region of this part. So we will be subtracting the value of Z equal to negative 0.24 from 1, because that is the whole area. We want this part. The part which is shown in shaded. That comes out to be 1 minus 0.4052, which is 0.5948. Or we can say that 59% of the learners or the students score above 500 in the GMAT. The average number of acres burned by forest and range fires in a large New Mexico country is 4,300 acres per year, with a standard deviation of 750. The distribution of numbers of acres burned is normal. What is the probability that between 2,500 and 4,200 acres will be burned in any given year? We have mu equal to 4,300 and your standard deviation, that is sigma, equal to 750. Two conditions of Z are given to you, that is 2,500 and 4,200. So we will be finding out the Z scores in respective cases. For 2,500, Z is equal to minus 2.40, negative 0.13. So we will be plotting it on the table. So first of all, we draw a horizontal line. Anywhere on this line, we draw a center line. And along that, we draw a bell-shaped curve. X is equal to 4,300, that is the center, 42 the left side, 25 more on the left side. And this can be easily evaluated from values of z. That is, z is negative, it will be no doubt it will be in the left side. 0.13 will be closer to 0, and negative 2.40 will be away from the 0. So in the area in between, this has to be evaluated. So your probability question says probability between 2500 and 4200 acres. That means 2500 less than x less than 4200. Transform it in terms of z. It will be negative 2.40 less than z less than negative 0.13. Now we have to find the probability. What we will, how we will do? We will break this. That means you can see we have to find the area of the shaded region. The probability is z less than negative 0.13 minus probability z less than negative 2.40. Getting the values of z equal to negative 0.13 and z equal to negative 2.40 from the table, we will simply subtract it. So that will be 0.4483 minus 0.0082, which comes out to be 0.4401. That means the probability between 2500 and 4200 acres that will be burned in a given year is 44%. What we have learned, exponential distribution is found to be useful for characterizing uncertainty in machine life, length of telephone calls, etc. These are the examples where these are applied. Normal distribution is found to be useful for characterizing dimensions of machine parts, heights, weights, etc. Now we move to unit 8, that is decision theory. Mathematically, how decisions are taken, because we had just recently completed probability. And when decisions are taken, so for coming up to a conclusion, we use data, statistics, and then at last we use probability. A necessary condition for the existence of a decision problem is the presence of alternate way of action. What else can be done? Each action leads to a consequence through a possible set of outcomes, the information on which might be known or unknown. One of the several ways of classifying decision problems have been based on this method about the information on outcomes. Decision making under certainty. The information on outcomes are deterministic and are known with certainty, and decision making under uncertainty is decision theory. Here, the information on outcomes are probabilistic. We are not sure with the probabilities known or unknown. Depending on the planning horizon under consideration, as also the nature of decisions, we have either a single stage decision problem or a sequential decision problem. Marginal analysis and DT approach. DT is decision tree approach. Marginal analysis for solving such single stage problems. For sequential decision problems, the decision tree approach will be used. In both the marginal analysis and the decision tree approach, we will be using the expected profit as the criteria for our decision. Expected monetary value, in short, we call it as EMV. EMV does not take into account the decision maker's attitude towards risk. Preference, on the other hand, preference theory provides us the remedy in this context by enabling us to incorporate risk in the same setup. The other problem with expected monetary value is that it can be applied only when the probabilities of the outcome are known. For problems where the probabilities are unknown, one way out is to assign equal probabilities to the outcomes and then to use EMV for decision making. However, this is not always rational, and we will find other criteria are available for decision on such situations. Marginal analysis, a technique widely used in business decision making and ties together much of the economic thought. In any situation, people want to maximize net benefits. That is, net benefit is equal to total benefit minus total cost. Then comes the control variable. To do marginal analysis, we can change a variable, such as quantity of goods you buy, quantity of output you produce, or the quantity of input you use. This variable is called the control variable, where we can change or manipulate. Marginal analysis focus upon whether the control variable should be increased by 1 unit or not. What is the key procedure for using marginal analysis? First of all, identify the control variable. Determine what the increase in total benefits would be if one more unit of the control variable is added. This is marginal benefit of the added unit. Then comes to determine what the increase in total cost would be if one more unit of the control variable is added. That is marginal cost of the added unit. If the unit's marginal benefit exceeds or equal to its marginal cost, then it should be added. For key procedure for using marginal analysis, remember to look only at the changes in total benefits and total cost. If a particular cost or benefit does not change, ignore it. And what does this work? Because marginal benefit is equal to increase in total benefit per unit of control variable. That is delta TR divided by delta Q, which is marginal revenue. Marginal cost is equal to increase in total cost per unit of control variable. That means we can say that marginal cost MC is equal to delta TC upon delta Q. The change in net benefits will be total benefit minus marginal cost. Now the thing is that why does this work? When marginal benefit exceeds marginal cost, net benefits goes up. So the marginal unit of control variable should be added. Now comes how the problem is formulated. A decision problem is characterized by decision alternatives, states of nature, and resulting payoffs. The decision alternatives are the different possible strategies the decision maker can employ. The state of nature refers to future events not under the control of decision maker, which may occur. States of nature should be defined so that they are mutually exclusive and collectively exhaustive. Another thing is influence diagram. An influence diagram is a graphical device showing the relationship among the decisions, the chance events, and the consequences. Square or rectangles depicts decision nodes. Circles or ovals depicts chances nodes. Diamond depicts the consequences nodes, and lines and arcs connecting the nodes shows the direction of influence. Next concept is payoff tables. The consequences resulting from a specific combination of a decision alternative and a state of nature is a payoff. A table showing payoff of all combinations of decision alternatives and the state of nature is a payoff table. Payoff can be expressed in terms of profit, cost, time, distance, or any other appropriate measure what we are using in the problem. Decision tree is a chronological representation of the decision problem. Each decision tree has two types of nodes. Round nodes, which correspond to the state of nature, while square nodes corresponds to the decision alternatives. And the branches, leaving each round node represents the different state of nature, while the branches leaving each square nodes represent the different decision alternatives. At the end of each limb of a tree are the payoff attained from the series of branches making up that limb. Just think over image of a tree. It's expands like this. With this, we will be concluding this session.